So the topic of today is deep learning, right? I know that many of you have been waiting to hear about this particular topic, so I'm glad that we had enough time to study this together. And why are we here, right? In terms of the narrative of the class. So the class has had a narrative, right? And at some point we realized that we have to do learning, right? We have realized this multiple times, but at least in the case of mini-max, when we were learning the utility function, as well as in the case of reinforcement learning, when we realized that we have to generalize from the seen states to the unseen states, we recognize that we need to do learning, right? Because the number of states in the world is going to be exorbitantly high, so high that it may be more than the number of atoms in the universe, but still humans can deal with that, right? If I take the scene in front of me in a very high fidelity camera, the number of pixels will be of the order of whatever 100,000s actually, right? And if you think about the RGB values for each particular pixel, 256 cross 256 cross 256, right? That would be the number of possible states for one pixel raised to the power 100,000 for the total number of possible images with this kind of fidelity, right? So even if we just look at images, right, there will be just so many possible images, but humans are pretty good at understanding them. So humans don't have an issue with that. The human brain is extremely good at classifying images. So the question that a lot of AI researchers, right from the very beginning, so this is not a new development, by the way. There have been at least 3 generations of neural networks. Not only have there been 3 generations of AI, where this is what we have discussed at least, that earlier it was more logical, then it was more probabilistic, and now it is more neural. But actually the neural networks themselves have been present throughout these 60, 70 years. So the most interesting thing is that most of the algorithms that people do use today in neural networks are algorithms that were developed in the 80s and the 90s. They were seminal algorithms which were ahead of their times at the time, right? Today we have realized the importance, right? And we'll talk more about that. But the intuition has been that, okay, AI is hard, machine finds it hard to understand images, understand speech, understand text, whatever, but humans find it very easy. So what is it that is going on in our brain, and if we can learn something from there, can we put it in the machine in order to make a better AI system? And so the intuition was, let us see what the brain has, right? And a brain has a massively interconnected network of 10 to the power 10 to 10 to the power 11 neurons, right? 10 billion neurons. But not only is it the number of neurons, but it is the amount of parallelism in these neurons that make the brain very different from a machine. In machine, many things happen linearly, the amount of available memory is much limited. You can't do parallel computation because CPUs can only do, right, so much parallelism, but human brain can, right? So there were a lot of attempts at saying, okay, let's say assume brain consists of neurons, these neurons are connected in this network. What is this neuron, and can we model it computationally? Can we create a mathematical model for a neuron and then build it up from there? So the first intuition that you get is, what is a neuron? Well, a neuron is something where a lot of inputs come in from different neurons or from sensors, right? And those inputs get processed into the nucleus of the neuron, and from there an electric pulse goes out to other neurons. This is sort of what a neural fundamental unit of a neural connection is in a brain, right? And while all of these are gross approximations, it was found that output spike, how much electrical signal do I send or whether I send a signal or not, is roughly dependent on the total strength of the inputs that were received by the neuron. So if a very strong input comes in, then a strong output goes out. If a very weak input comes in, no output goes out. And so we said, okay, I mean, this doesn't seem very hard, so let us try to model it mathematically. Let's create an artificial neuron. Okay. And in this artificial neuron, let's say that it has some inputs. For example, let's say there are binary inputs, -1 or 1, representing, let's say, true, false, right? And then what we would do is we would give each input weight, some weight. We will not say that all inputs are equally important. Some inputs may be more important because they are coming from the eyes, and some inputs may be less important because, let's say, they are coming from the nose, or vice versa. Right. So you will say that, okay, some inputs are more important, some are less. I will give weights to each input. And I will also say when should I send the output out. So I will create a threshold for that neuron. And this can be represented in this kind of a schematic where I have a summation of all the inputs, but not the original inputs, but weighted sum of inputs. And then I pass it through a threshold, that is it greater than mu I or not. And if it is, we will output +1, otherwise we will output -1. And my function, if you think about it, a single neuron would be considered as a function from all the UIs or XIs, whatever is your variable for inputs, to an output, single output, sending 1 or -1. And it would be, and theta x is defined as it's 1 if x is greater than 0, and if it is -1, it is if it is less than or equal to 0, then it is -1. Right. And if you think about it, this is actually a function, and it's a function which in your mind you should be thinking, oh, I want to create a function from my board state or my reinforcement learning grid world or whatever it is to something. Right, and that something could be your Q value function, your policy function, or whatnot. So eventually I need to learn a function, or everything can be casted as a function, right? Everything is a function. And now we can't learn the function exactly because the number of inputs is humongously large, so we have to approximate. To approximate, we have to define some structure over this function, and we can learn the parameters. Like we did in Bayesian network, we defined the structure using a Bayesian network, and then we said what are the probabilities. Well, we can learn it from data. So we will define the architecture, or we will define a structure of my function approximator, and then I will learn the parameters. For example, in this very simple artificial neuron, what are the parameters? The weights and the threshold. These are the parameters for this very specific function approximator. Is this a linear function? Is this whole thing which goes from the inputs to the outputs, would you call it a linear function? Is it a linear function? No. What do I have to do in order to make it a linear function? There should not be any threshold. See, this sum is a linear function. But as soon as we say, okay, if your sum is greater than mu I, output 1, else output -1, we have lost the linearity. Now there is a non-linearity here. This unit of a neural network, artificial neural network, is called a perceptron. Okay, that's the technical term for it. This is probably the first artificial neuron that was developed by AI researchers. Okay. Of course, in our brain we don't have a single neuron. We have a interconnection of neurons. So that is called neural networks, where you have many inputs and then they go into these artificial neurons and they have a connection between them, and finally you output the final output that you want to output, and that's called a multi-layer perceptron. You can also have a single layer perceptron where all the inputs go to one layer of neurons and then you give the output. So that's a single layer neural network. Now, the first thing people said, okay, that sounds pretty good, and we can now start to emulate the brain. Let us try to understand what it can and cannot represent. Let's say I want to do classification. Let's say I have a set of inputs and I want to know whether they are in the class 1 or they are in the class -1. So there are two classes and I want to find some separator in the input space between the two classes. Right? What kind of functions can it represent and what kind of functions can it not represent? So the first important observation that was made in this context is a function that is linearly separable can be computed by a perceptron. For example, suppose I take the AND function. So, these are my inputs. Now I will be in the -1 and 1 world rather than 0 and 1 world. So if it's -1, -1, I want to output -1. If it's 1, -1, I want to output -1. But if it's 1, 1, I want to output 1. So in other words, I want to output these 3 points as -1 class and this red point as +1 class. So if you look at it more carefully, there are many different ways to do this, right? There may be one separator which may be like this, like a curved thing in the middle. There may be one separator which may come from somewhere, goes like this, and then finally comes through. There can be many such separators. But what perceptron computes is a linear separator. For example, if W1 is 1 and W2 is 1 and threshold is 1.5, then this creates this particular linear hyperplane. Why? Because if both of them are 1, then the sum is 2 and that's greater than 1.5. If both of them are -1, then this is -2, so plus 1.5 doesn't take it, sorry, it's not greater than 1.5. Even if one is 1, the other is -1, it's still 0, it's not greater than 1.5. Everybody with me? So this is good. We can compute the AND function using a perceptron, we can compute the OR function using the perceptron. What about the XOR function? There's a question, yes. No, the question is, will it always be from binary to, two class problem? No, we'll generalize it. Generalize the heck out of it. Any kind of input, any kind of output, we'll do a lot of things. In fact, that's all the modern neural networks is all about, but we are building it slow, right? So, can we compute the XOR function? I want to compute the XOR function. What is the XOR function? The two class problems. So both of them are same, output the class 1. If both of them are different, output the class -1. Let's say the XNOR function. Why don't we? Sure. That's okay. You are saying convert -1 to 1 in U2? Yeah, that can be done. Won't change anything. XNOR becomes XOR. That's the same. It's the same thing, right? So, can we compute it using a perceptron? What do you think? Yes, Sukriti. We cannot do this with a perceptron, she says. Why can we not do this with a perceptron? Because you are using a term which we haven't defined, but that's a correct term. What's your name? Shaurya says, because they are not linearly separable. What does that mean? It means there does not exist a linear surface, a line or a hyperplane in a higher dimensional space, which can separate the positive class from the negative class. You can try it. Can you come up with any line? If you make a line here, the red green is here, red green is here. If you make a line here, then red is here and both greens are here. You have to make sort of like a curved surface if you want to separate the reds from the green. Now that put cold water on research in neural networks. This was a very famous theorem by Marvin Minsky's in his book on perceptrons, where he showed, Minsky and Peppert, showed that perceptron with a threshold unit fails if classification task is not linearly separate. Well, it feels very obvious in hindsight, right? Because we are always computing a linear function and then we are saying, are you greater than a value? Or you can take the value into the linear function and say, are you greater than 0? Well, if you look at it, this space above this black line is when this value is greater than 0, and this space below the black line is when this value is less than 0, or you can check it here, for example, for this blue line. So a perceptron eventually is saying, look, there is a linear thing, and if you are greater than 0, that's one region, if you are less than 0, that's another region, and that's it, right? And so we can only deal with linearly separable functions, which is not interesting, because in the world there are highly nonlinear functions, right? We are in Delhi today, it's the pollution time. If we wanted to predict what is the total amount of pollution or AQI value or PM 2.5 value that a particular place will have, depending upon its wind speed, depending upon the time of the day, depending upon whatever, right? Would it be a linear function? Or if in the best world, you gave a very complicated board position and you said, okay, should everything depend linearly to the final value? Well, it does not, right? And a linear function would be a gross approximation. So people said, no, we want to do better. We want to go beyond the linear functions and we want to come up with nonlinear functions and a representation that can handle the nonlinear function, right? So there are two methods to deal with that. The first method is the idea of a multi-layer perceptron. What is a multi-layer perceptron? It says, no, don't just take it through one perceptron and give me the output, take through layers of perceptrons. For example, just two perceptrons, one after the other, can help us solve the XOR function. We can look at it. It says output X plus output Y minus 2 times the output X plus Y minus 1.5. If it is greater than 0.5, output 1, else output minus 1. Now it will take you some time to figure out what's going on. So let's look at the lower neuron. When does it send 1 out? It sends 1 out when both of these are 1. Otherwise it sends minus 1. You can check that, right? This is the same AND function actually here. Now it sends minus 1, that means in one case the contribution would be minus 2, in other cases the contribution would be 2. But in the case when both of these are 1, you will get X plus Y minus 2, which would be 0. So it will not be greater than 0.5. In all other cases, this term itself would be 2, and the other terms would be either 0 in case they are different. If they are different, it will be 0, so that will be greater than 0.5, so you will send 1 out. In cases where they are both minus 1, then again they will be cancelling out, because it will be 2 minus 2, oh sorry, minus 2 minus 2, which will be minus 4, again it will not be greater than 0.5. So in the two cases where you have 0, 1, you get these two terms cancelling out and this 2 taking over, and in cases where, in all other cases, you will have a 0 output or a negative 1 output. You can double check that at home. this just two perceptrons can actually compute the XOR function. So while the Minsky and Papert theorem said, we don't want to work on neural networks, it can't even represent a non-linear function, after a few years, people started coming back to neural networks because they realized, oh, there's a very small fix. But then, if you have these layers of neurons, it was not easy because they had to then think about how do I learn the weights. Learning of weights becomes complicated, and we will talk about that in the next class. For now, we are just understanding the expressiveness of the model. Okay. So what does a multilayer perceptron do? In order to understand this, let us look at this particular example. This is a very good example. Except now, for some slides from now, I will put the threshold inside as a further input, right? You can always say that x plus y greater than mu can be written as x plus y minus mu greater than 0. So that minus mu is what we will call the bias term. So we will just put the bias in the input. Okay. So this is let's say a multilayer perceptron. Let us think about what is it doing. So the first neuron, the pink neuron, says half x minus y plus 1 should be is the input, right? Now it will have greater than 0 or less than 0 values, and if you draw the line of that particular neuron, one side of it would be positive and another side of it would be negative. One side would be positive 1, the other side would be minus 1. Similarly, if you look at the other neuron, which is the orange neuron, one side of it would be greater than 0 and one side of it would be less than 0. So here, if you think about it, this is the part where orange is 1, this is the part where orange is minus 1. Similarly, this is the part where pink is minus 1, this is the part where pink is 1. Now, let us check out the specific function pink minus orange minus half as the output function. Pink minus orange minus half. Let me show you the answer, but we can think about it together. This is the function that the green is computing. This is the final output. But where would it be 1 and where would it be minus 1? We need to think about that now. So where would it be 1? Let's think about that. For it to be 1, pink minus orange needs to be greater than half. Because these are outputs 1 and minus 1, pink has to be 1 and orange has to be minus 1. In all other cases, that would not be the case. So that means that at least in this example, the green will send 1 in this region where the two lines are creating a non-linear region. So this is now a non-linear function. Green is a function that separates this green region and this white region. So just by having two layers of neurons or perceptrons, we were able to compute this non-linear function. In fact, and this is the interesting part, there is a universal approximation theorem that says that given enough number of neurons, any two-layer neural network can approximate a given function with arbitrary closeness. Neural networks is such a general representation that just by two layers of neurons, I can represent or I can really well approximate any function whatsoever. Linear, non-linear, highly complex with many different regions, whatever. Just two layers. That is the beauty and the power and the expressiveness of a neural network. Anyway, so this was our idea number 1, to deal with nonlinearity. The other idea is a notion of activation function. So what are we saying so far? We are saying that your inputs go through a linear combination and then we check it with a threshold. And if the threshold is greater than something, then we output 1 or we output minus 1. So we are sending a very discrete output out. We are sending 1 and minus 1, very discrete. But then people said there are many problems with sending the discrete output. First of all, it cannot compute a continuous function like, you know, a random function 3.7, right? It can't do that. So there's a problem there. The other problem is that this perceptron is highly nonlinear, which basically means and non-differentiable. So which basically means the gradient here is 0, the gradient here is 0, and in the middle at the point the gradient is undefined. So like nothing is going on. I can't figure out how I need to change my weights in order to get the function to do what it wants to do. So perceptron is very difficult to train. It's practically impossible to train. Nobody uses perceptron. Well, okay. At least you cannot use gradient based methods to train perceptrons. There are different methods to train perceptrons. There are good methods also. But you will study in a machine learning course. So I'll backtrack. I wouldn't say that nobody uses perceptrons, but I will say that in the modern neural world, perceptrons are not used very often. And yes, there exist training algorithms for perceptrons, but we will not talk about them. We will say, well, we want the gradients to be slightly better defined. So instead of a all 1 and sudden drop and all -1, let us make it smoother and continuous. And we do this by the notion of an activation function. So instead of saying either we send the signal out or we don't, or we send -1 or +1 out, we are saying that we will send a continuous value out. And the common activation functions are logistic activation, ReLU activation, ReLU stands for rectified linear unit, and hyperbolic tangent activation function, in short known as the TANH function, the tan hyperbolic TANH function. Okay? I will very quickly talk about these. Again, this is not a full-blown deep learning course, so I will very briefly give you intuitions about each of these activation functions, so that when you talk to somebody, you can come across as somebody who knows things, but you don't know many things. Just clarify. Okay? So the sigmoid function says 1 by 1 plus e to the power minus x. Output 1 by 1 plus e to the power minus x, where x is the cumulative weighted sum of the inputs. So if you carefully plot this curve, you find that this curve is always between 0 and 1. It starts out being at minus infinity is 0, you can check. So if you put x equal to minus infinity, what do you get? 1 by 1 plus e to the power infinity, which is infinity. So that is 1 by infinity, which is 0. So at the limit, it starts out with 0, and check what happens at x equal to infinity. You get 1 by 1 plus e to the power minus infinity. E to the power minus infinity is, limit is 0. So you get 1 by 1 plus 0, you get 1. So in the limit of minus infinity and infinity, you get 0 and 1. Let us check out x equal to 0. It's a good point to check. So at x equal to 0, what do we get? 1 by 1 plus e to the power 0. E to the power 0 is 1. Please, these are silly questions, but it just tells me that you are listening or not listening. E to the power 0 is 1. 1 by 1 plus 1 is half. So what is it saying? It is saying separate your inputs into two regions, one where it is less than half, one where it is greater than half. It sort of, actually if you plot the curve, it remains very close to 0 for the longest time, and very close to 0 around -4, it starts to go up. It goes up till around 4, and then it becomes very close to 1 and stays 1 throughout. Okay? And you can think of it as a neuron which is not firing, not firing, not firing, not firing. Ambiguity region, doesn't know, maybe I should fire with small probability, maybe I should fire with higher probability, maybe I should fire with even higher probability. Now I am sure I should fire. Fire means send the signal out. Okay? So, if you think about gradients, the gradient very close to values 10, 20, 30, x equal to 10, 20, 30, what is the gradient? Very close to 0. It less than x less than -20, less than -10, what is the gradient? Very close to 0. When is the gradient interesting? Somewhere between -4 and 4. Okay? So this is not an ideal algorithm, I mean ideal activation function, because a lot of gradients are 0, but there will be some problem with every activation function. So we'll keep moving. The other function is just take this 0 to 1 curve and expand it vertically between -1 to 1. So how do you do that? You take the original curve, you multiply it by 2 and subtract 1 or something like that. So this is called the hyperbolic tan function. This is the smooth approximation of the perceptron function. So perceptron was between -1 and 1, but a very quick sudden jump, a ladder jump. This is the smoother version of that. In my intuition, you use tan h function when you have to say, I have a positive influence on you, but I can also have a negative influence on you. But when you talk about sigmoid function, I use it when I only say, I have a positive influence on you or no influence on you. And my influence is also bounded in both these cases. But that intuitions you will generate over time. Then there is something called the rectified linear unit. It's a linear function, but there is a non-differentiability at 0, where you say that from 0 and below that, it's all, I will not send any signal out, but in greater than 0 point, I will send a linear signal out. So in the region 0 to infinity, it's a linear function. In the region -infinity to 0, it's a linear function. Such functions are called piecewise linear functions, but they are not, it's not a fully linear function, right? It's a non-linear function. The good news here is that your gradients in the positive region don't saturate. Your gradients don't become 0. Your gradient is 1 or -1. So that means that until you are in this positive region, you can keep training this weight much better, and we'll talk about training later. So it was found that rectified linear units and networks of rectified linear units can train much better than networks of, for example, sigmoid units. Okay. By the way, this problem where your gradient goes close to 0 and your your model doesn't train is called the gradient vanishing problem, or the vanishing gradient problem. So vanishing gradient is a term. It's a technical term. If you are hearing it for the first time, I encourage you to go to Google or Wikipedia and read about it. It's a very important phenomenon in making these deep neural networks train well.